The next section is completeness property of R. That is the completeness property of set of real numbers. So let us see some definitions. So it is the definition of the set which is bounded above or bounded and also bounded below. So the definition is, let S be a non-empty subset. S is non-empty subset of set of real numbers R. Then the set S is bounded above if there is a number U which is a real number such that X is less equal U for all X in S. And this is definition of bounded above set. And each such number U is an upper bound of S. That means, for example, if this is a real line, if I have some set which is subset of S, right? If I have this set as a set of these real numbers as a subset S of R. So what does it mean a set is bounded above, or what does it mean an upper bound of subset S? So what is the definition? Set S is bounded above if there is a number U such that X is less equal U for all X belongs to S. It means that a set is bounded if there exists real number U for which all the elements of set S are less than U. That means if I choose U from this place, if this is U, so it is true that all the elements of set S are definitely less than U. Right? If I choose U to be the element situated here, in this case also all the elements of set S are less than U. Right? If I choose U to be element situated here, in this case also all the elements of set S are definitely less than or equal to this U1. So according to definition, this definition of bounded above set, the element U1 or the element U2 or the element U3 can be worked as an upper bound of the set. Right? What is the definition? There should exist some real number U for which all the elements of set S should be less than or equal to that real number U. And in this case, there exist real numbers U, U1, U2, U3 and many more. So what we can conclude from this case? So upper bound may not be unique. There may exist many upper bounds for the set, right? So, and one more thing, upper bound, if this real number can be an upper bound for the set, this real number can be an upper bound for the set S. So, and the largest element of the set can also be an upper bound for the set. That means we can say that the upper bound may or may not belong to the set, right? So the remark is an upper bound may or may not belong to set S. The next definition for bounded below: the set S is bounded below if there is a number, a real number L in R such that L is less equal X for all X in S, and each such number L is a lower bound of set S. So again, similarly, if this is a real line, suppose these elements denotes subset S of real numbers. So what the definition says, a set S is bounded below if there is some real number L such that L is less than all the elements of set S, right? A set is bounded below if there exists some real number L so that L is less than or equal to all the elements of set S. So if I choose a real number L to be placed here, so can it work as a lower bound for this set S? Definitely yes. Why? Because by the definition of bounded below set, this real number L1 is less than, strictly less than all the elements of set S, right? If I choose a real number L from this place, it will also work as a lower bound for the set. If I choose lower L, a real number L at this place, it will also work as a lower bound for the set. If I choose the smallest element or minimum element of the set S, then also this element L will also less than all the elements of set S, right? So in all the cases, each element will work as a lower bound for the set. So what we can say that again, the remark will be, again, in this case, a lower bound may belongs to the set. In other three cases, the lower bound, not necessarily it is in the set S. A lower bound may or may not belongs to set S. Now next definition is bounded set, bounded and unbounded set. A set S which is subset of R, subset of real numbers, is said to be bounded, is said to be bounded if it is both bounded above and bounded below. Bounded above and bounded below. That means upper bound should be exist for the set and lower bound should be exist for the set. Then we can say that the set is bounded. And when the set is not bounded, a set is unbounded if it is not bounded. A set is unbounded if it is not bounded. For example, let us see some examples. I have set A with the elements 1, 2, 3, 4. So, what can be the upper bound and what can be the lower bound for the set? Then, upper bound. What can be the upper bound? 5? Yes, 5 can work as upper bound. 4.5? Yes, 4.5 can be work as upper bound. 100? Yes, definitely. 1000? So, 4. What about 4? So, by the definition of a set bounded above, all the elements of the set A are less than 4. So, 4 can be also an upper bound for this set. So, upper bound 4 or any number greater than 4 can be an upper bound for this set. What will be the lower bound? 1. Definitely all the elements of set A are greater than 1. Any other number less than 1? 0? Yes, 0 can be also a lower bound because all the elements of the set are greater than L or 0. So 1 or any number smaller than or less than 1 can be a lower bound. So the set A is bounded above and bounded below. Bounded above and bounded below. Therefore, set A is bounded. This is next example. Example 2. If I choose a set to be 1, 2, so upper bound can be 2 or greater than 2. Any real number which is equal to 2 or which is greater than 2 can be an upper bound. Lower bound 1 or any number less than 1 can be a lower bound for this set B. The next set, if I choose C to be 0 to infinity, so upper bound, I cannot find a real number so that all the elements of this set are less than that real number u. So it does not exist. Therefore, u upper bound does not exist for this set. What about lower bound? It exists and it can be, it exists and it can be, and it can be any real number 0, it can be 0 or any real number less than 0. Okay, so you can try for the sets D equal to minus infinity to 2. The next set you can try for the set 1 by n such that n is integer. Then you can try for the set 1 by n square such that n is natural number. Okay. Let us move to the next definition. which is supremum or infimum. Supremum and it is not or and infimum. So let S be a non-empty subset of set of real numbers R. So let us see the definition of supremum. If S is bounded above, then a number U is said to be a supremum, or it can be identified as least upper bound, or in short it is least upper bound, LUB, of S if number 1, U is an upper bound of S, and number 2, if V is any upper bound of S, then U is less equal V. Right? So we have seen in the definition of above bounded set and upper bound, we have seen that if this is a real line, if this is set S with some elements from R, any real number greater than this U, or largest or maximum possible number of the set, can be an upper bound for the set. So all these elements can be upper bounds, but the least upper bound or supremum is what? So U is real number U is supremum or least upper bound of set S if U is one of the upper bound, and second thing, if V is any other upper bound, then U should be less than or equal to V. That means if U is supremum or least upper bound of set S, if U is itself an upper bound of S, and any other upper bound of set S should be greater than U. That means U must be least of smallest of all the upper bounds of set S. Right? So if this is the set of all upper bounds of set S, so what can be the least or smallest of the upper bound? This U. Right? And the next definition is infimum. If S is bounded below, then a number L is said to be an infimum or greatest lower bound. Greatest lower bound, or in short it is GLB of S if number 1, L itself should be a lower bound. L is a lower bound of set S, and number 2, if R is any lower bound of S, then this R should be less than or equal to L. That means what? Similar to the definition of supremum, a real number L will be infimum or greatest lower bound of S if, I will explain here, this can be a lower bound, this can be lower bound, this can be, so these are all possible lower bounds. Right? So a real number L is least infimum or greatest lower bound of set S if L is a lower bound, and if R is any other lower bound, then L should be greater than all the lower bounds, right? That means L should be greatest of all the lower bounds of set S. So let us see example. Number 1, if I have set 1, 2, so what can be supremum of set A? So upper bound, 2 can be upper bound for this set, 2.5 can be upper bound, 2.8, 2.9, 3 or any other larger number can be upper bound. But what is the least of these upper bounds? The number 2. So 2 is the least upper bound or supremum of set A. So what can be infimums of set A? Similarly, 1 can be a lower bound because all the elements of set A are greater than 1, greater or equal 1. Any real number less than 1 can be a lower bound. What I want? Infimum, that means greatest of those lower bounds. So greatest of all those lower bounds will be 1. So supremum for this set is 2, infimum will be 1. Second example, if I take set -1, infinity. So what can be supremum? The lower bound itself does not exist because I don't have any real number which is greater than all the elements of the set. Right? Because the set is not bounded on the right side. It goes to infinity. So supremum does not exist for this set. What about infimum? Yes, definitely. Infimum is -1, and observe between these two sets. Infimum is 1, but 1 does not belong to this set. For this set, infimum is -1, and it belongs to the set. It is why? Because here it is open bracket, it does not include element 1. Here it is closed bracket, it includes -1. Next set, if I choose elements 1 by n such that n is natural number. So what the elements of this set will be? So the elements, if I choose n to be 1, so it will be 1 for n equal to 2, it is half for n equal to 3, it is 1 by 3 and so on. Right, so as n increasing, the set is decreasing. So what can be the supremum and infimum for this case? So supremum of C, it will be the largest element. So if I choose element 2, so it can be upper bound. Element 3, it can be upper bound. If I choose element 1 or real number 1, it can be upper bound. So what is the least of upper bound? It is 1. And it belongs to set C. What about infimum C? So this is the set of real numbers in some decreasing order. So it is 1 by 3, 1 by 4. The value of this fraction is decreasing. So ultimately it will decrease up to 0, but definitely it will not become 0. It will be non-zero, 0.0 point something it will be there. So what can be the lower bound? If I choose 0, real number 0, so 0 can be upper lower bound. If I choose any real number less than 0, it can also be a lower bound. So what is greatest of the lower bound? 0. And note that 0 is not there in this set. 0 is not in this set, but even though it is an infimum of set C. So let us go to the completeness property of R, set of real numbers. The completeness property. So every non-negative set, every non-empty set S of real numbers that has an upper bound also has a supremum in R. So this is the completeness property of set of real number. Every non-empty set S which has an upper bound, it also must have a supremum in R. So the analogous property, this is the property with upper bound or supremum. The analogous property can be written as by involving the lower bound and infimum, every non-empty set S of real numbers that has a lower bound also has an infimum in R. And the next thing is the Archimedean property. And the property is that if x is real number, then there exists a natural number nx. This x is suffix, it is not as a variable, a natural number nx, such that x is less equal nx. So simply what the property says, if we choose any real number x, then there exists a natural number n, such that our chosen x will be less than or equal to that natural number. It is not that much difficult, it is very easy property. The next one is corollary. If S is 1 by n, such that n is natural number, and we have shown that, then infimum of S is 0. So no need to give proof, because we have seen this as an example. So the next thing is density, the density theorem. The density theorem. If x and y are any real numbers, with x less than y, then there exists a rational number. R, such that x is less than r is less than y. So what the density theorem says, if we choose x and y to be any real number with this property, x should be less than y. So this theorem says that if you choose any two real numbers with this condition, x is less than y, so there must exist a rational number which will lie between x and y. Okay? And corollary to the theorem is, if x and y are real numbers with property x less than y, then there exists an irrational number. Then there exists an irrational number z such that x is less than z is less than y. So similarly, because rational and irrational are between, it says that between any two rational number there is a irrational number, between any two real number there is a rational number, between any two real number with the property that x should be less than y, there is an irrational number. So let us see example. Find an irrational number between 2 and 3. Between 2 and 3. So how we can find? So suppose if I choose a real number 100 and in other side I choose a real number 200, and definitely 100 is less than 200. So if I choose this, so the example is, find irrational number between root 2 and root 3. Find a rational number between root 2 and root 3, and I choose two real numbers to be 100 and 200. So what I should take? Suppose I take 169 in between 100 and 200. Is it true that 100 is less than 169 is less than 200? Yes. So now I can write it as, how I can write it is, I can write it as 50 less than 75, and which is the perfect square between these two? 64. Yes. So I can write it as 25 into 2 less than 64 less than 25 into 3. So I can write it as 2 less than 64 divided by 25 less than 3. Right? So now taking square root, it is root 2 is less than, it is the square of 8, and it is square of 5 is less than root 3. So 8 by 5 is a rational number between two real numbers, root 2 and root 3. I can have any other options also. Suppose I can have 32. You can choose any pair, and then 48. What is the perfect square in between these two? 36 or 36, yeah. So I can write it as 16 into 2 less than 36 less than 16 into 3, and then it can be written as 2 less than 36 upon 16 less than 3, and taking square root, it will be root 2 less than 6 by 4 less than root 3. So it is also true. You can have many more pairs to find out a rational number between two real numbers.